So I'll try to demonstrate you the variety of exoplanets and show that on one hand there are many different, sometimes very peculiar examples of these objects. On another hand, we know already enough to say that not everything is possible. There are many options to have exoplanets with different properties, with different sets of parameters, but still there are some basic things, and the main task is to understand these basic things. So I'll try to underline them when I come to these points. So at first, let me define what an exoplanet is. We have to separate exoplanets from other types of objects. And the first step is to say that an exoplanet is a planet orbiting another star, so not our sun. So this means that planets in the solar system are not called exoplanets, they are our planets. On another hand, if you have an exoplanetary system and then, for example, you take one planet and separate it, make it isolated, then it is not called exoplanet anymore. Another thing is to define what a planet is. And this plot will help us to do. In the very beginning, I have to tell you that these funny numbers you can find on nearly every slide of this presentation. They are related to numbers of papers in the archive on the website archive.org, and the first four digits, they represent the year and the month. So this particular plot was taken from the paper published in November 2014, and then this is the number of the paper during that month. Okay, so this means that if you are interested in details, you always can refer to particular papers, and these references are encoded in these numbers on every slide. So let's discuss this plot. On the horizontal axis, we have mass of an object in Jupiter masses. So 1 means 1 Jupiter mass, 1000 means 1000 Jupiter masses. And for example, this green dot here represents our Sun. So our Sun is roughly 1000 times more massive than Jupiter. On the vertical axis, we have a radius of an object. I always say an object because here we have objects of different kinds, mainly planets, brown dwarfs, and stars, but planets can be separated in several groups. So let's start from the top right part of the plot. So here we have stars. This is the branch which represents stars. We can also continue it to slightly higher masses, but the important thing for our discussion is the existence of the lower mass limit of stars. Here it is. Why is it so? We define a star as an astronomical object in which thermonuclear reactions are going on, so hydrogen burn into helium. And to let hydrogen burn in the thermonuclear reactions, you understand that burn is not real burning, which is related to oxidization, but here we have nuclear reactions. And to let hydrogen burn, we need high temperature and high density. And a star is responsible for this temperature and pressure in its interiors by itself. So this is due to the stellar mass that deep in its interiors there are high temperature and pressure. And if we decrease the stellar mass, then at some point temperature and pressure in the center are not enough to let these thermonuclear reactions to start. And so we have this lower limit for stars. Roughly, it's about 80 Jupiter masses. What then? Then still we do not have planets, we have another type of objects, brown dwarfs. Brown dwarfs are some intermediate objects between planets and stars. In brown dwarfs we have so-called degenerate interiors, and it is possible that there are some thermonuclear reactions, but they are not related to the main chain of reactions going in the sun, for example. So normal hydrogen, which is very abundant in the universe in general, and also in stars, in brown dwarfs, in massive planets. So this hydrogen is not participating in these reactions. So we have brown dwarfs till another critical mass, which is about 12 Jupiter masses. So this is the upper limit for planets. Astronomical objects with masses below 12 Jupiter masses can be called planets. Then you can define if they are really exoplanets or free-floating planets or something else. But here we have planets. Massive planets are made mostly of hydrogen and helium, that we will discuss in details further on. So we slowly move towards lower and lower masses, and this green dot is Jupiter. So one Jupiter radius, one Jupiter mass, Jupiter. Then we go further on to lower and lower masses, and we see kind of transition from gas giants, so planets made mainly by hydrogen and helium, to planets of lower masses, which later on will be dominated by ices. Ices doesn't mean just usual ice made out of water. It can be also frozen methane, frozen CO, CO2, and other molecules which can form kind of ices, so we call them ices generally. But still, normal water ice is very abundant in the universe. Of course, at high pressure it changes its properties, but still it is ice made of water. So this green dot is Saturn. Then we move towards the lower left corner of this plot. Here we have ice giants, Uranus and Neptune. And finally we have rocky planets, and these two green dots is Venus and Earth. So we see that there are different types of planets, and all symbols in this plot are already known planets. By the way, not all known planets, they can be much more, and this can result in slightly more scattered plot. But for us here and now, the most important is to understand these different dependencies of or interdependencies of parameters of planets, and to come closer to this variety of types of exoplanets. At the moment, we know several thousand exoplanets, and there are many candidates. And these two plots represent some general properties of this population. I want to underline here that here I'm talking about known exoplanets. Of course, we not randomly discover exoplanets. There are so-called selection effects. We discover those which is easier to find. That's an important thing. At first, let's look at the plot on the right. So here we see distribution in distance towards the host star. And of course, it depends by two main things. At first, it is difficult to discover very, very far away planets. So there are some not well-defined upper limits on this distance. So at some distance we see less and less planets. And this distance is about 1 kiloparsec. 1 parsec is roughly 3 light years and a quarter. So this roughly means that its maximum is at 3,000 light years from us. And the second effect is that the main part of planets in this plot are discovered by the Kepler satellite. So the satellite observed a particular patch in the sky, and in this patch there are not so many nearby stars. Of course, when you look in this cone at further distances, you have more and more stars, and so we don't see many planets around us. To find more planets around us, you have to focus specifically on nearby stars, and this can help, but of course this is a separate research program. Okay, just to summarize, the main thing is that if we take a random planet from a catalog, then typical distance would be 1, 2, 3,000 light years, which is a lot, by the way. So this means that it's not an easy task to study exoplanets. So we have to separate two things: to discover an exoplanet and to study it. Studying is a little bit, well, not a little, difficult task in comparison with just finding out that a planet is there. Okay, then let's have a look on another plot here. On the vertical axis we have planet masses in Jupiter masses. On the horizontal axis, distance of the planet from its star. So roughly the radius of the exoplanet orbit. It's given in astronomical units. Maybe I have to remind you that the astronomical unit is the distance from the Earth to the Sun, which is roughly 150 million kilometers. So we see that mainly we know planets which are relatively close to their stars. That's because it's easier to find planets which are closer to the stars. This is related to a very simple idea. Later we'll discuss different methods. For many methods, it's important to see repetitions. It's necessary to see several events of different kind, different methods, several events to identify securely that we really see a planet. We really see signs of the presence of the planet, let us say, because typically we don't see the planet itself. We see some effects, we observe some effects it produces. Then we see that there are some peculiar planets that are not existing in the solar system. In particular, this group, which is called planets, they are called hot Jupiters. So we see that they are as massive as Jupiter. Well, some can be more massive, up to the upper limit. Up to the upper limit, and they are very nearby to their stars. Again, we see them not because they're very abundant, but because it's very easy to discover them. How do we discover planets? There are several methods. They're listed here. So then I'll start to discuss these methods one by one. What I want to say here is the following thing. We'll also discuss it with some plots later. That different methods at the moment provide different numbers of planets. So some of these methods are very fruitful. And we find many hundreds of planets because of them with the help of these methods. Some methods are not that effective yet, but on one hand, these methods like astrometry can become very productive soon, in next 3-4 years maybe. Also, different methods can help you to find planets with different parameters. What we want is not just sport-like behavior, finding more and more planets. We want to find planets with different parameters to understand the whole picture of planet formation, evolution, and for that we need different methods with different selection effects, which all together help us to make this picture of the universe of exoplanets. The plot just shows the number of planets discovered during different years, starting from the very beginning of the exploration. And you see that there are two strong peaks here. They are related to two data releases of the Kepler satellite, which is the main contributor to the known population of exoplanets. Okay, so let's look at another plot. Here, planets discovered by two main methods are shown. So only planets discovered by radial velocity variations, these blue dots, and these orange dots, planets discovered by transits. So we'll start with two methods, and we'll see that up to now they help to discover planets occupying very different parts of this plot. So historically, the first method of discovering exoplanets around normal stars. Normal means solar-like. Solar-like means not exactly like the sun, but stars with hydrogen burning in their interiors. So historically, the first method was related to radial velocities of stars. The idea is very simple. We don't see the planet. But let us imagine that we have a very simple situation, a star and a single planet. Both of these bodies move around the center of mass of the system. It's marked by the cross. Of course, the star is much more massive, so it lies much closer to the center of mass, but still, with the same orbital period, the star is moving along this ellipse. And when we observe the star, we see that we see it from detailed studies of the stellar spectrum. We see that half of this period the star is moving towards us and half of the period is moving from us. We can measure just the radial velocity. Velocity is of course oriented somewhere in 3D, but we see the projection on the line of sight. So that's what we call radial velocity, radial from our point of view. And in this graph, we see the velocity variation for the first discovered exoplanet, 51 Pegasi b. And we see this nice sinusoidal-like velocity variation. It's not always sinusoidal-like. People were very lucky to find this planet because the orbit is nearly circular. Then the eccentricity is very small, as you can see. We are situated nearly in the plane, in the orbital plane of the planet, and the orbital period is very small. The orbital period is slightly above 4 days. So it helps to measure the whole oscillation, the whole variation during a very short period of time, so during a week. And then you can have many repetitions to measure it more and more precisely and to understand that this is really due to a planet, not due to some pulsations in the star or something else. So that's the first discovered extrasolar planets. One of the last example of an exoplanet discovered by this method, which really hits the mass media, was the discovery of a planet around Proxima Centauri. Proxima Centauri is the closest star, so actually the name Proxima means the closest. And the star itself is a tiny red dwarf, so very low mass and low luminosity star. The planet is also small, so it might be a rocky planet. It's slightly more massive than our. And it has an orbital period just 11 days, but as the star is so small, it emits less energy, and this orbital period corresponds to the distance which is inside the habitable zone. So this planet is particularly interesting, and really it's a kind of luck that the first discovered, the only discovered planet around the closest star is situated in the habitable zone. And that's really very interesting and very promising, maybe. Okay, now the second method, which is the most effective now, is related to planet transits, and it was discussed by many authors, but the first wide discussion was given by Otto Struve in the middle of the last century. But at that moment it was impossible to use this method because you need a very high precision of measuring the light from the star. So what we measure we just make photometric measurements for this star. So we measure its magnitude, we measure the energy flux from the star. If a planet is projected on the disk of the star, then we see decrease in the brightness of the star, because it's a black dot over a very bright disk. In its orbital motion, the planet starts to cover at first part of the disk, so we have this decreasing part of the curve. Then it comes to the disk. The disk is not uniform. This is a kind of projection effect. We're not going to discuss it, but the stellar disk looks for us not uniform. Its central part is much brighter. So the planet is moving along the stellar disk. We see this minima, and then this transit ends. So that's it. The point is that planets are much smaller than stars. And if we compare, for example, the size of the Earth and the size of the Sun, then the Earth is roughly 100 times smaller than the Sun. But here we have to compare not sizes, but areas. And area is radius square. So if we compare the area of the solar disk and the Earth disk, then the factor is not 100 but 10,000, and it's very difficult to measure a drop in the magnitude of a star, which is 1% of 1%. Still, it is possible, especially if you make observations from space. And with the help of space observations, we know many planets, and the last interesting example is the system called TRAPPIST-1. First planets in the system were discovered by the system TRAPPIST-1, which is on the Earth. It's not a space system, but more planets in the system were discovered with the Spitzer Space Telescope. And so space observations contribute a lot to discovery of exoplanets with this method. Then the third method, it's the method of gravitational microlensing. We know that general relativity is the geometrical theory of gravity. So gravity is about curvature of space-time. Every body curves space around it. And light propagating near the body feels this curvature. And every body, in this sense, works like a lens. So if an observer, here he or she is, observes a star, here is the star, and another body, which we'll call lens, is passing just in between, so not in the center in terms of distances, yeah, but it means that it has to appear on the line of sight or very close to the line of sight. So as it passes, it works like a gravitational lens, and we observe enhancement of the flux of radiation from that star. So the maximum is reached when the lens is in the closest position to the line of sight, and then it continues its movement, and we see a drop. But if the lens is double, if there is a second body, second light body in comparison with the main lens, then we can see additional peak here, and this would be the signature or the presence of another body. We can measure the light curve and then recalculate from it properties of the secondary body. And it can happen that parameters, actually we measure the mass. The mass of this secondary body is in the planetary range. Then we say that we discover an exoplanet with gravitational microlensing. So let's look at real data. In relative, we have a binary lens. We can have many additional features, not just one. And here is one example. But here we have even two additional bodies, two planets. And parameters of this system slightly resemble parameters of the solar system in the sense that we have the central star, which is more or less close to the Sun. I mean, in terms of its mass. Solar light. And we see two planets. One has a mass close to the Jupiter mass, and another has a mass close to the mass of Saturn. But of course, we want to see exoplanets. It's very difficult, still it is possible in several cases. Just to give you some numbers, we know thousands of exoplanets, and there are just tens of cases in which we can have direct images of exoplanets. So in less than 1% cases, we really see the planet. But some examples are really peculiar, well, not peculiar, they are very impressive. And the most impressive one is the system called HR 8799, in which we observe 4 giant planets orbiting its star, and when you put several photos together in one movie, you can see how these 4 planets rotate around its host star during several years of observations. It's very spectacular. Sometimes we find really peculiar systems. For example, we know that there are many binary stars, many double stars. There are also triples, quadruples systems, and so on, up to systems made of 6 stars. And we discover planets in these multiple systems. But if you have interaction of several bodies, then not every orbit will be a stable one. Already in binary systems, there are many unstable orbits. But if you discover a very young system, and we have a selection effect, it's easier for us to discover young giant planets because they are brighter. They are still contracting, they are shrinking, and this results in additional release of energy. So we can discover a young system which is unstable, but it is not destroyed yet. And the system in this plot is such a system. So this is an exoplanet, directly measured exoplanet in a triple system. So let's start from the right image. It's a composite image. We have a binary. We have the third star, and all 3 form a unique system. They are gravitationally bound with each other. And here is the planet. Of course, it's called B because planets numbered starting from the letter B, from the small letter B. And this planet has an unstable orbit, but the system is very young. It will be destroyed later, and the planet will become a free-floating planet, a vagabond planet. So we observe even such rare, peculiar systems. Okay. So here I finished the first part of my lecture. In English I speak much slower than Russian, so I have a lot to tell you further on, but here I want to summarize the variety of exoplanets we have. We have hot Jupiters, we have rocky planets, super Earths, hot Neptunes, ocean planets, which doesn't mean that it resembles a drop of water. Actually, interiors are under high pressure, and we have inside ice of a very special kind, which even we cannot reproduce in our laboratories. We cannot obtain such high pressure in the laboratory. We have peculiar chthonic worlds, evaporating planets, which are too nearby to their host stars, so their atmospheres are evaporating under the action of strong flux of radiation from the star. So we have a huge variety, and we want to put it in one evolutionary picture, which is of course possible. Look at the biological world. There are many very peculiar animals of different kinds, and plants also, sometimes very peculiar, but we can put them inside one evolutionary picture. We know that all animals on Earth have one common ancestor in faraway past. Of course, planets do not have one common ancestor, but planets can be reduced more or less to the periodic table of elements and to some physical laws which drive the process of formation of planets. Okay, I told you already that there are planets in binary systems, in triple systems. This is the example of a planet in a quadruple system. I will not stop here, so I'll move further on. I want to compare efficiency of different methods in discovering exoplanets. Here we have orbital distance again on the horizontal axis and planet mass on the vertical. And different symbols correspond to different methods. What we see that transient planets, known transient planets, mainly have very short orbital periods because we need many repetitions, well, at least several. And mostly these planets were discovered by the Kepler satellite, which had the duration of its program of observations just 4 years. So with Kepler, it was very difficult to find a planet with an orbital period larger than 1 year, and impossible to find a planet with an orbital period larger than 2 years. So they are separated. They are situated in the left part of the diagram. The method of radial velocities actually is not more effective in finding planets at larger distances. Simply, it is applied already for 20 years, 25 years. So some stars are monitored for more than 20 years in this hunt for exoplanets, and it allows to find planets with large orbital period, with large orbital separations. To observe a planet directly, you really need to see a planet separately from the star. It means that they must be separated in space. So we can find only planets on very wide orbits with direct images. Luckily here we don't need any repetitions. We in HR 8799 we see how planets are moving around, but it's not necessary to identify them. And here we see planets discovered by direct imaging. Then lensing. Lensing is effective because you find the planet very rapidly. You don't need repetitions, and it allows you to find planets at larger distances. This is the only effective method now to find planets with lower masses and large distances from the star. Also, it's the only method to find really a Jupiter-like planet, because Jupiter is an old planet. It doesn't shrink significantly, so this additional energy release is not very effective. With green triangles, planets of the solar system are marked, and it's visible that it's very difficult to find really twins of our planets. So Jupiter can be found by microlensing and by long-term monitoring of radial velocities. Forget about Neptune and Uranus, and forget about Mercury and Mars. But planets similar to Earth and Venus potentially can be found by transits, and maybe soon can be discovered by radial velocity measurements. That's another comparison. Also, future projects are marked here, especially projects related to microlensing. And you see this gray area here, and these lines here on the right plot, they correspond to proposed projects to discover exoplanets with microlensing. These might be space projects, and if they are realized in the next, say, 10 years, then we'll come to the era of planets discovered by gravitational microlensing. Okay, but what we want as a next step is to study planets as physical objects. So we want to know what is inside. Now we are more in the situation like medicine many hundreds years ago, before they really made dissections and looked inside human bodies, what's going on there. Then people step by step got opportunity to make such studies, and it of course made huge progress in medicine and physiology. But now we want to make another step and look at, say, non-normal anatomy. And For exoplanets, again, we're back in, I don't know, 12th century. We can just measure masses and radii of these planets, orbital parameters, that's it. And we have to reconstruct their internal properties starting from this not very abundant data. So just to remind you what we have mass measurements, orbital distances, and we can measure how much energy a planet gets from its host star due to light, due to radiation. But still, even with this simple data, we can have some guesses about internal structure of exoplanets, because, as I told you, not everything is possible. There are several typical compositions, there are limiting cases, which are represented here. So planet radius on the vertical line, planet mass on the horizontal line. Here, please note that mass is in logarithmic scale in the units, and radius is not, it's linear scale. Radius is not changing that much. So this variety of planets can be explained in the first place by variety of composition. What we have? We have, at first, let's start with two limiting cases. We need to take elements which are abundant in the universe. That's very important. The most abundant elements are hydrogen and helium. So very massive planets might be made mostly of hydrogen and helium, because that's, say, the only option. So T is mainly made of water, as you know. So the limiting case is actually the stellar composition, which is here shown with the Z equal 2%, because the Sun is made of hydrogen and helium for 98%, and 2% are for heavier elements, starting from carbon. So Z2 is solar composition. Then in the lowest part, here we have solid planets. And among solid elements, there is one specific one, which is actually iron. Iron and nearby elements, nickel and cobalt. So iron is the heaviest abundant element. So there are, of course, heavier elements, gold, for example, or platinum or something else, but they're not very abundant. We hardly can imagine a planet made out of gold, unless somebody made it artificially. So naturally formed planets, the heaviest one, can be formed only from iron. So we can draw a line how the radius depends on mass for pure iron composition. Pure iron is an idealization. There'll be a mixture, and the mixture is a rock. So this composition corresponds to rocky planets. The next step towards less dense planets is a planet made of ice, and I told you that there are different kinds of ices, but the water ice is the most abundant. Water is a very abundant molecule in the universe, because it's made of hydrogen, which is in the first place in abundance, and oxygen. Oxygen is in the third place. So it's a very abundant molecule, and it represents, by its physical properties, ices in general. And it helps to, then you can have a mixture, an iron or rocky core, then a layer of ice, then a maybe thick atmosphere made of hydrogen and helium, and you can feel everything between iron line and this solar composition line. What about these planets? This is more tricky, but we know what to do. We can take a planet, a gas planet made mostly of hydrogen and helium, and start to heat it. What's the source of heat? A star. The host star of a planet can heat it, and then this gas ball starts to expand. And that's how we can obtain planets with masses about, say, a mass of Jupiter, or maybe few tenths of percent of the Jupiter mass, but which are inflated by a factor of 2. So factor of 2, it's not like something incredible. The volume is increased by a factor of 8, maybe up to 10. It's not that much. But still, it's interesting, and what's more important, it's observed. But before we come to exoplanets, let me briefly and rapidly remind you structure and composition of the solar system planets. So this is Mars. Its internal structure more or less resembles the Earth structure. There is an iron core, then mantle, and relatively thin crust. Neptune. Neptune is an ice giant, and it has 3 main layers. It has a rocky core, then huge ice mantle, which actually contributes the main part to the total mass budget of the planet. And then a thick atmosphere made of mainly of hydrogen and helium, but also some other gases are there. What I have to say, the first, this ice mantle, it doesn't resemble the ice from your fridge, for example. It's ice because it's water or methane or something at lower temperature and high pressure. So it's ice in this term, but it's a different kind of ice. The second important thing, which actually is not so pronounced in English, but when it's translated to Russian, it's a disaster. Typically, when people see rocky core, they translate it as a stone core. And stone immediately tells you that it's something, you know, like Jeffrey Talley, thick as a brick. So it's something solid. It is not so. Because of very high pressure and temperature inside Neptune, the core is made out of heavy elements, but it's not solid. That's important. Then Jupiter, again, core of rock metals, but it's not solid because of high pressure and temperature. And very, very thick and heavy atmosphere. I don't know, it's the main body of the planet. You can't call it just atmosphere. It's made mostly of hydrogen and helium. Hydrogen is in a very funny physical state. It's called metallic hydrogen. It doesn't mean, again, that it is solid, because metal typically have associated, well, for many people metal is a kind of music, but still, typically people imagine something like a metal tube, metal pipe, something like this, or a metal bar. It's not like that, it's gas. And of course, there are outer layers of the atmosphere, which gives Jupiter its nice appearance with the stripes and spots, including the big red spot. Mercury. Mercury is peculiar because it's it has a very heavy metal core. I don't know if there is a metal band called Mercury, but that will be a good choice for many reasons, actually. Why is it so? Why propulsion is so atypical? We don't know exactly, but most probably Mercury, soon after its formation, when different compounds were separated, so heavier elements sinked into the interiors, it had a collision with another body, so it lost part of the mantle, but saved all its metal core. And that's why propulsion is shifted. And Saturn more or less has composition similar to the Jupiter one. Okay. About the composition, I want to underline that in the solar system, and it's typical, definitely, in the solar system, only gas giants, only Jupiter and Saturn, are dominated by hydrogen and helium. All other planets, including Uranus and Neptune, are dominated by heavier elements. When we talk about planets, so let's start with general planets. There are 3 main ingredients, and I'm still promoting that it's a nice title to a rock album: ice, rock, and gas. Ice, rock, and gas are 3 main ingredients from which you can make planets. And people like very often to demonstrate this composition in so-called ternary diagrams. So it's a it's a more complicated way to plot than to have 2 axes. You have 3 axes now. You have rock, ice, and gas, and you have to put a planet in this coordinate system. Even if we talk about Earth-like planets, again, for them you can have three main type of ingredients. So iron, silicates, and well, water means, again, ices in general. It can be not just water, but water is the most abundant and among them. And again, if we put a dot somewhere here, we can say that this planet is made, say, well, that would be a very peculiar composition. Lots of ices, water, significant amount of iron, and very small amount of silicates. But still, 3 is a very important number for planetary structure for this discussion. So we have 3 main types of planets because we have 3 main ingredients. We have gas giants, icy giants, and solid planets. And in the solar system, we have examples of all 3 types of planets. Of course, you can have different proportions, and then more difficulties appear. And in the solar system, we don't have very peculiar planets, or maybe we consider our planets not so very peculiar and find peculiar examples in other systems. Still, I want to say that there are planets very atypical in comparison with planets of the solar system, but they might be made of the same 3 main ingredients. So again, ice, rock, and gas. Of course, you can put it in a physical model, put the model in the computer, and calculate artificial population of planets. People do it. It's a very important approach to study, well, different objects, including exoplanets. So here we see results of this calculation. Typically, when you see some very accurate lines, it means that these are not observations. This is something artificial. Here we have planets of different kind in comparison with some observed examples shown with dots with error bars, which represents uncertainty in the measurement of mass or radius. It depends what was actually measured. And we start with light planets, which mostly are made of iron and silicates. And as we increase mass, we have larger fraction of ices here, shown in blue. And finally, a higher fraction of hydrogen and helium, so stellar elements. And so they are shown in red in the yellow. Here is a similar plot. What is shown is the fraction of hydrogen and helium depending on mass of a planet in the model. So again, we see that as we move towards more massive planets, hydrogen and helium start to dominate because they are just more abundant in the cloud, in the material out of which the star and the planetary system around it were formed. It's interesting to redraw mass radius plot into mass density plot. It's shown here. And again, we see 3 types of planets. Here it's very clear. A, these are rocky planets. B, icy planets. And from F to G, these are gas planets. In between, there are also some intermediate cases. They are not very often found in observations. They are more rare cases. We don't see anything intermediate in the solar system, but with the variety of planets we already discovered, we have some funny examples. Why massive planets have gas-dominated composition? Because as a planet grows in the protoplanetary disk, at some mass, it starts actively to capture gas from the disk. Initially, it's too light; it cannot capture gas. Imagine you, I don't know, you bought on eBay an asteroid for some funny reason. Actually, legally, you cannot do it, so it's a very stupid thing to do. But still, you bought an asteroid. You are in some faraway future. You bought an asteroid. You want to fly there. You come to the asteroid. You brought some balance, some oxygen with you to make an artificial atmosphere. If you just let the oxygen out, it will disappear in the outer space, because your asteroid is not heavy enough to capture the atmosphere. So initially, as the planet grows, it's not heavy enough to capture a thick atmosphere. But at some mass, which is slightly larger than the Earth mass, a planet starts to capture gas very efficiently, and it starts to become a gas giant. And we roughly know at which mass it happens. It happens at 4 Earth masses. We see it in observations, because what we see that the radius of the planet increases, density is growing initially, but then density starts to fall down. Why? Because from faraway distance, when we observe exoplanets, we see not their solid surfaces, we see outer layers which are not transparent. So just we see the opaque area, opaque part of the atmosphere, and it corresponds to some radius. We can recalculate it to mass, and we come to the conclusion that at roughly 4 Earth masses, the composition of the planet typically is changed. But you see, there is a line, and there are many scattered points around it. Of course, we see different examples of planets, because protoplanetary disks are not equivalent. Even inside the same disk, there are different positions with different parameters. So it all brings you some variety. But of course, if you compare two guys from Brazil and from Finland, most probably one is playing football and another is playing hockey. Everything can happen, but still, that's a rule, and a similar thing is applicable to exoplanets. Okay, I wanted to tell you more about super Earths, but I see that I don't have much time. So, just briefly, there is a type of planets called super Earths. They are not found in the solar system. We try to understand why. Maybe really there is a reason for it. So super Earths are planets in between of, say, Earth and Neptune. So they are intermediate planets. They might be made out of rocky materials and ice in different proportions. So typically, planets slightly more massive than Earth, they are really super Earths. And planets closer to Neptune, they are sometimes called mini Neptunes. Because it's expected they are dominated by ice in their composition. As this type of planet is a mixture, say by definition, then they show a variety of properties, and I prepared many talks about it, but I think I quickly skip them, stopping just at some particular cases, especially at this one. So I want to demonstrate that actually it's very difficult in this mass range to know the precise composition. So let's have a look at this line of planets with 5 Earth masses. So different planets have different composition, and these are idealized compositions. And we see that only very unrealistic pure hydrogen planets can be distinguished by their large size. But even if you have a peculiar planet made of carbon monoxide, and you compare silicate planets or water world, they have very similar size. It's very difficult in real observations with real precision, which is not infinite precision, to find difference between them. So, of course, in such cases, we are in a difficult situation. We cannot precisely say what these planets are made out of. But what is important, and I really want to come to this point with a more detailed discussion, planets are formed from protoplanetary disks with very mixed composition. You can't have pure carbon planets, because carbon is not somehow separated from other elements in the protoplanetary disk. You always will get a mixture. If you just take a mug and take some water from, I don't know, Gunk River, it will not be just pure water, and I don't recommend you to drink it. because everything, well, many things are mixed in this river. Okay, so I'll skip these nice plots about super Earths. And I want to stop on this slide, focusing just on the right plot. I want to say that despite the fact that we can measure only masses and radii, still we can make reliable models of internal structure for many planets, because typically very limited, we have in a very restricted conditions of formation. We want these planets to be made in realistic protoplanetary disks. We observe them. We have direct information about many protoplanetary disks now. I'll show you later. And that's why we can have some educated guesses about composition and internal structure of many planets. So now we come to the third topic I wanted to discuss, planet formation. So the general idea is known, and it's the same from Kant and Laplace time. So you have interstellar medium, some fragment of the interstellar medium start to collapse because of its own gravity. So it's cold and dense enough to collapse under its own gravity. So it starts to shrink, and finally it forms one massive body, a star in the center, and there is a disk around. Why a disk? Because initial fragment was rotating. So as it is shrinking, the angular velocity is increasing. And for many parts of this fragment, it's very difficult to move towards the axis of rotation. So it's much more easier to go down in the, say, equatorial plane of the system. And that's why you have a protoplanetary disk, and initially a planetary system might be relatively flat. So no miracle that we have zodiac. We have a set of just 13 actually constellations on the sky, in which we can find the planet of the solar system. You cannot find Jupiter in Cepheus or Cassiopeia, for example, because they are far from ecliptic, far from the plane of from the orbital plane of the Earth. And other planets have their orbits very nearby, nearly parallel, but nearly with the same orientation as the Earth orbit. Okay, I told you that now we have many images of protoplanetary disk. I'll show you just some of them. There are many more. The main instrument is the interferometric system called ALMA, situated in the South America, because they need very special condition for observations. They need a very dry air. So it's a mountain desert in South America, and there are many astronomical instruments there. Another good place, well, good to observe, is Antarctica. And now more and more telescopes are built in Antarctica. So we see this protoplanetary disk, sorry. And we see interesting structures inside them, and these structures mostly are directly related to the existence of forming massive exoplanets inside these protoplanetary disks. So let's start with a very simplified picture of planet formation. So let's say the old view, which people plotted like 30 years ago and before to describe the solar system formation. So we start from the moment when we already have a protostar, and we have a protoplanetary disk, initially gas and dust, so two main ingredients, gas and dust. Gas, mainly hydrogen and helium, and dust can be of different kind. I'll tell you about it later. Gas and dust are well mixed. Step by step, dust start to separate from the gas because dust particles are heavy, so they sink towards the plane of the disk. And this dust starts to agglomerate, to form small structures, dust particles stick to each other. Actually, you know, if you don't make cleaning in your flat for, say, 2 weeks, then you see that planets are starting to form in the corners, behind furniture and so on. So if you wait for a million years, maybe a planet will appear there and life on it, definitely. So we start with the small structures, and they grow, and finally they become rocky planets, or they become rocky cores of future giant planets. And now we come, at some point these cores, if they are massive enough, they start to capture gas. So they start to accrete gas from the disk, form atmospheres around the core. I told you that there are two types of dust, because heavy elements which can form dust can be either rock elements, silicates, iron, carbon, so on, and they can be ices. Ice dust cannot, of course, be formed, cannot exist close to the star, because it's too hot. So close to the star, you have only dust made of iron, silicates, carbon, and similar elements. And so in the solar system, close to the sun, Earth-like planets were formed. So you see here 4 of them. Then there is a critical distance behind which it's cold enough so ice dust can be formed. It's very important because ices are more abundant. That's why we have icy giants, but we don't have rocky giants. So behind this critical line, which is called snow line, behind this line, planets can grow faster because they have more dust to start with. They can grow faster and they can reach higher masses. That's why giant planets typically start to form behind the ice line. That's very important. So the ice line is a very important concept. Of course, as we have different ices, corresponding ice lines are situated at different distances, but still they are very close to each other. And inside, again, I really think we won't have to start make t-shirts out of this. You have metal and rock. Okay, so we start with dust, and we relatively quickly come to the size of asteroids. There are some difficulties, there are some uncertainties in theoretical scenarios, there are many interesting problems, many puzzles still to be solved, but people are actively working in this direction. As we reach kilometer size of the growing object, we reach a milestone. So very often bibliographic systems send emails. You reached a milestone, your paper reached some amount of citations. So we reach a milestone. What happens? If two, say, small stones collide, they produce dust, small pieces, and these dust and small pieces are lost. But if two, say, kilometer-sized objects collide in the protoplanetary disk, they can be destroyed. But gravity is already strong enough to keep this matter from spreading out. And so from this size, objects start to grow effectively because of collisions. So that's a very important step on the route, on the track of forming Earth-sized planets. Maybe I'll skip modeling of this oligarchic growth part. As we reached the stage when a solid core has a mass about several Earth masses, then we can try to form a giant planet. The problem is that you have to do it quickly, because gas from a protoplanetary disk is very rapidly evaporated. Well, rapidly, in a few million years. Few million years, it's not that much for a planetary system. So if you are rapid enough to form planets with Earth size, then you can move further on, you can form more massive planets. because the reservoir of gas is still there. But if you made a heavy planet in 10 million years, then you cannot grow much more because you don't have gas anymore in the protoplanetary disk. So these might generally work for all planetary systems, and if we make such a plot for architecture of planetary systems, we see that many planetary systems are similar to the solar one, but with one important thing. It looks like they are all shifted towards the star. So the picture I showed you before, let me come back. This picture is generally correct, but then you take all these planets and move towards the star. So it means that planets are moving in the protoplanetary disk, and in many systems they move significantly. You can ask why this didn't happen in the solar system, because of course it's vice versa, a kind of anthropic principle works. If it happened in the early solar system, then most probably there'll be no life in the solar system, because Earth would be shifted closer to the Sun, so out of the habitable zone, and in the habitable zone we'll have ice giants, for example, and of course there'll be no life on ice giants. So migration of planets is an important thing, and it's a very important ingredient of modern models of planetary formation. That's an example how planets migrate in the systems. This is a very simplified approach, because in this model, in one planetary system, there was just one planet. So one planet is not influencing other planets in this model. And if we deal with small planets, shown in red, they do not migrate significantly. But when, for example, icy planets reach some critical mass, you see, icy planets are mainly formed at larger distances behind the ice line. Then they can start to migrate very rapidly and even fall down on the star. And it looks like we see examples when stars have some peculiar properties which we can explain by planetary migration and a merger of a planet and a star. So we can look how a planet evolves in a planetary disk and forms nice structure in the disk. So let me try to run the video. So we see here the planet starts to form, it grows, and what you see is the density contour. So lighter areas, lighter regions have higher density. And you see that even a single planet interacting gravitationally, just gravitationally, with a protoplanetary disk can produce a very beautiful picture. And actually, I want to say, because we're having this lecture on the festival which is related to art, I would say that the best science art must start from exact models, exact scientific results, because they can be very beautiful by themselves. And this, I think, is a very good example of such very nice picture you can have in realistic modeling of planet formation in the protoplanetary disk. Okay, so we have different planets and we have different methods to find them, and step by step with different approaches to discover planets, we start to find planets of different kind and learn more and more about planetary formation. So now I want to spend a few slides at the end of the lecture to discuss ongoing and future observations of exoplanets. So presently in orbit we have two satellites dedicated to exoplanetary studies. The first one is TESS. It's a satellite with a main task to discover more planets. So actually it doesn't study planets a lot, but this is a machine to discover planets. So it's expected that it will study 500,000 of stars. and discover thousands of planets around them. The main observational program, say the guaranteed observational program, is already finished, but the satellite is working. It's fine with the satellite, so it can work for several years more. So people are reducing data, and already now there are tens of planets discovered with tests, and there are thousands of candidates which will be confirmed soon. Another satellite working now is European Cheops. This satellite is not for discovering planets, but for studying. So the name of the satellite is an abbreviation. So you see the word characterizing. The idea is that people observe planets already discovered. Planets discovered with measurements of radial velocity variations are observed to find transits for the same system, and combination of two different methods for one planet allows you to obtain additional information about physics of the planet. So now, when it is possible for such planets, we have independent measurements of mass and radius. It is important because it gives us more confidence in discussions of internal structure and composition of these planets. The next big machine for planetary discovery will be Plato. It will be launched in 6 years, and it's expected that it will look for planets around million of stars, and so we expect that tens of thousands of exoplanets will be discovered by transit method, just by this satellite. So you see that in different periods of time, different methods are more effective than other. So the story of exoplanets started with radial velocity measurements. Then with the launch of Kepler especially, we entered the transit area. And now we are expecting for many results, for thousands or maybe even 10, 20,000 planets discovered by the Gaia satellite due to astrometric measurements. That will be very interesting. It will be a huge contribution to our knowledge of general properties of exoplanets. And then who knows, maybe some specific space missions for gravitational microlensing studies will be approved, and we'll enter another era, microlensing era of exoplanets. So we'll see. Everything happens relatively rapid in this branch of science. That's why it's so interesting. But in addition to just discovery of new exoplanets, we need detailed studies, and one of specialized satellites for it will be called Radial. It's approved. It's another European satellite. It will study atmospheres, so it will measure spectra of roughly 1,000, at least many hundreds of exoplanets, and unfortunately, it will not be able to measure parameters of Earth-like planets. They are too small, but will increase significantly our knowledge about atmospheres of giants and super-Earths. Then large Earth-based telescopes will be built in the next few years, in this decade. And there'll be 3 big instruments. One of them is GMT. It is formed, say, of 7 telescopes as big as the largest telescope now. So such 8.4 meters mirrors are now working on the, for example, giant binocular telescope, and here they'll work together, 7 mirrors as one instrument. Another telescope, which is still, unfortunately, at the stage of even not construction but planning the 30-meter telescope. Maybe you know that story. It'll be another telescope on Hawaii, and local people are against building this telescope on some particular spot, so there are some tensions with local religions. And finally, the first instrument which will start operating will be extremely large telescope. It's the largest instrument among these three telescopes of the next generation. So we expect that in 5 years it will start scientific observations, and it'll be effective in studying atmospheres maybe of even Earth-like planets. So it's expected that in several years of observations it will be able to detect oxygen in the atmosphere of an Earth-like planet in a habitable zone. That'll be very interesting. Finally, we are waiting for the next big space telescope, which will be James Webb Space Telescope. Now the plan is to launch it in 2022. Finally, of course, we have plans. And definitely the next big step would be to make space systems, because it seems that it's impossible to make such systems on Earth. Space systems which will allow us to obtain direct images of Earth-like planets in habitable zones. So there are two difficulties. Habitable zones means that planets are close to their stars, and so you need to cover the star somehow. So there are different techniques to do it, but you have to get rid of the stellar light to see a small blue maybe dot close to it. And then, of course, Earth-like planets are very dim objects. So you need space instruments, instruments of a very special kind. In any case, it'll be not one satellite, it'll be a system of satellites, and you need to put large telescopes in orbit because you want to observe very dim sources. But still it is possible. We don't need some technological miracles. We need significant progress. We need some new advanced technologies, but engineers tell us that it's quite possible to do. So there is no secret, say, how to make it. And optimistically, I would say that before the mid-century, some system of this kind will be in orbit, and then we'll have more information about how life is spread in the universe. Okay, so I'll stop here, and I'll stop with a list of papers which maybe can help you to enhance your knowledge, to make it deeper about different subjects I discussed in the lecture.